Okay, you guys. So we are going to do week 5, chapter 12, a teeny bit of chapter 12, and a little bit of chapter 13. In chapter 12, we're just going to cover unit cells and basic structures of solids. So we just really want to figure out how to calculate the density of a unit cell. I did post a video that someone else made on YouTube that does a really good job explaining what a unit cell is, and also explains the different types of unit cells. So if you didn't get a chance to watch that or you skipped over it, go back. It's a good one. And then chapter 13, we're just going to do solutions. So we will get into that. So types of solutions, solubility, factors affecting solubility, and preparing solutions. So that's week 5. Homework is listed right here. Notice that there's this little preparing solutions practice problems 1 through 5. So I have attached that as like a Word document. Just some extra problems because chapter 13 really doesn't give you like a basic preparing solutions practice problem. They're all kind of involved. And I really just want you to know how to do that. So there they are for week 5. Mastering Chem also has more examples of stuff from chapter 12 and from chapter 13. So make sure you check that out. And let's do this. All right, so again, hopefully you already watched that other video about solids and structures. Solids, remember, are the most dense form of matter. They're highly ordered, and they arrange themselves in structures that usually end up in pretty geometric shapes. A couple vocabulary words here or terms. Crystal lattice is just the arrangement of atoms within the solid. And what they want to do is they want to get close enough to each other because they're solid. They're going to be dense. They're going to be close to one another. They're going to have attractive forces. But also remember that they are surrounded by electrons, and so is their neighbor. And so there's also a component of repulsion that's there. And so they kind of want to get like close enough while still having their own personal space. And that all depends on size, type, whether these atoms are charged or not, and who they're crystallizing with. So this all depends on from crystal lattice to crystal lattice. And so usually they follow patterns, so they can kind of be categorized into different genres of crystalline solids. A unit cell. A unit cell is a small, repeatable unit of a lattice. So if you think of a tile floor, one tile would be the smallest repeatable unit of that tile floor. And so by studying just that small piece, we can get information about the whole thing, which is really big when we're considering how many atoms there are. Coordination number is just how many neighbors an atom has. So that's all that is. Okay, here's another definition or another illustration of a unit cell. So if you look at B here on the right, you have like this decorative tile, and every tile is the same, and one tile is just repeated throughout the floor. So this one tile is my unit cell, because if I look at this tile, I could describe the entire floor just by looking at that tile. And that's what we do when we look at the unit cell of a crystalline lattice. Okay. The first one is just a simple cubic structure where the atoms are aligned on top of each other and side by side. There's large gaps of open space simply because this is really not an efficient way of packing. They're directly on top of one another and they're directly aligned with one another, but it leaves a lot of open space. So here it is in 3-dimensional space. Again, this is open space that is not being used. So it's not the most efficient packing. We have 1 atom per unit cell because 1/8 of each atom is at each corner. And so that adds up to 8 because there are 8 corners. A length is 2 times the radius. Your coordination number is 6, meaning that each atom has 6 nearest neighbors. And we have a 52% packing efficiency, which honestly isn't that efficient. So we don't really do a whole lot with simple cubic, but that's just what it is. A body-centered cubic is a little bit more functional. You basically have kind of an every other pattern where these guys are aligned just like you would have in a simple cubic, but now your spaces are filled with extra guys. All right? So those spaces are now full and there's less extra wasted space. Here it is in three-dimensional structure. You can see these guys in the center that are taking up that space that normally would be open. All right? But these guys are still right on top of each other. And so, so are those. They're all aligned and they're right next to each other. Okay. So in a body-centered cubic cell, you have 2 atoms per unit cell. And the length of one side is 4 times the radius over the square root of 3. That square root sign's kind of funky, so. This would be given to you on an exam. You just need to know what to do with that information. Your coordination number is 8, meaning that every atom has 8 neighbors, and is much more efficient, or at least more efficient than simple cubic, with a 68% packing efficiency. So that's body-centered cubic. Face-centered cubic is like if you took some marbles in a jar and started filling up the jar with marbles. This is how they would align themselves. They kind of fit into the grooves of the layer. So you have a single layer. The next layer kind of fits into those grooves. And then the third layer fits into those grooves that the other one makes. And you just continuously pile these on. So none of them are really aligned. They're kind of just fitting into the open spaces of the guys above them. And that's face-centered cubic. So for this, you have 4 atoms per unit cell. And your length is 2 times the square root of 2 times r. This is not 2 root 2r. Like, do not take the square root of r with 2. It's just 2 root 2, and then multiply that by the radius. I did it the other way, and it doesn't work. And I was annoyed, so don't do it. Your coordination number is 12, so there's tons of neighbors. Everybody's all over the place, and there's a 74% packing efficiency, which just shows you how much more efficient this is as a way to pack than the other two. So this is face-centered cubic. And again, this information that we need to know what to do with would be given to you on the quiz or test. All right, you guys, what we need to do is we need to figure out the density of a crystal structure depending on the type of unit cell you have, and then you'll be given some information about either the radius or the length, and we can calculate the density. Remember that density is mass over volume. So what we need to do is we need to calculate the mass, which we can do, and we also need to calculate the volume. So the mass is kind of how much stuff you fit in, and the volume is where you put that stuff. Volume we're going to find from the length. Remember that volume is length times width times height. But in a cube, length equals width equals height. So the volume is just going to be length cubed. So once we can solve for the length, then we cube it, we get the volume, and we can just plug it in to find the density. So we use 2 pieces of information from our unit cell. We're going to use how many atoms per unit cell there is, and also what the length equation is. So let's solve this problem. So we get iron. Iron is Fe. If you look up the molar mass for iron on the periodic table, you get 56 grams per mole. This was a body-centered cubic, which means I have 2 atoms per unit cell, and my length is equal to 4r divided by the square root of 3. So that's information that I just have from the problem. I also am told that the radius is 124.1 picometers. A picometer is super, super small. It's 1 times 10 to the minus 12 meters. So it's just how they measure it because it's really small. Okay, let's solve for A. So you start with 2 atoms. What I'm going to do is I need to convert atoms to moles, and you do that using Avogadro's number, and that's atoms per 1 mole. Okay. That was from Gen Chem 1, just a conversion factor to get from particles or molecules or atoms to moles. Now we got to go from moles to grams, so we know how to do this. We just use the molar mass. Moles cancels, atoms cancels, we get some really, really small mass. Because right now, this is the mass of 2 iron atoms, so it's really small. Okay, we got it. There it is. B. We got to find the length, and we got to find the volume. So, length is equal to 4r over the square root of 3. So, L is equal to 4 times 124.1 picometers divided by the square root of 3. What that gets me is 286.6 picometers. But nobody uses picometers when we're talking about density. Nobody. So we need to convert from picometers to centimeters. How do we do that? So we got to relate them both to meters. So if I just use this conversion every time, so I know that there are 100 centimeters in a meter. So 1 times 10 to the 2, that's 100. And I know that I have 1 times 10 to the 12th picometers in every meter. If you do 1 times 10 to the 2 divided by 1 times 10 to the 12, that is going to get you centimeters from picometers. Picometers cancels, and you end up with 2.86 times 10 to the minus 8. You're usually going to have something to the minus 8 centimeters. There's my length. Hooray. But I need my volume to solve for density. So remember we said, all right, well, I got to cube my volume to find, cube my length to find volume. So if I take 2.86 times 10 to the 8 cubed, I get 2.35 times 10 to the minus 23 cubic centimeters. Awesome. So here's my volume. Okay. See if we can get one more pen change. Oh, we can. It's too green. Let's see if we can make this go away. All right, now I need density. Remember, it's mass over volume, so I go ahead and I find my mass. And I go ahead and I throw in my my volume. Cubic centimeters. 7.9 grams per cubic centimeter. All of that, and we get 8. That is the density of my iron. And that's it. You're always going to get like a normal number. You're not going to get some crazy number with exponents. Okay? Find the mass. Start with your 2 atoms. Find the volume. Use your length equation. And then we go ahead and plug in to mass over volume is density. And that's that. All right, you guys. Here's number 2. Your turn. Gold is crystallizing with a face-centered cubic unit cell. So this is face-centered cubic, so you got to go ahead and figure out what your parameters are. Here's the radius. You need to look up the molar mass of gold, which is AU. All right. Pause. Figure it out. All right, you guys, here it is. Here's the answer. So I looked up the molar mass of gold is 197 grams per mole. So you start with the 4 atoms. I got 4 atoms because a face-centered cubic unit cell has 4 atoms per unit cell, and its length equation is 2 root 2 times r. So I start with my 4 atoms. I divide by Avogadro's number, multiply by my molar mass, and I get in green my 1.31 times 10 to the minus 21 grams. There's my mass. Now I got to find volume. Remember, volume is just length cubed. So I got to find length. I'm given R. R is my 144.2. So I do 2 times the square root of 2 times 144.2. I get 407.9 picometers. But I don't want picometers. I want centimeters. So I got to do one more conversion. And I get my length, which is here. I cube that. And I get my volume, which is there. Now, I just divide to find my density. So I plug my mass in the numerator, my volume goes in the denominator, and I get 19.3 grams per cubic centimeter. And that's the answer. All right, you guys, one more. We have lithium in a body-centered cubic structure. Now we are given the length. This is different. We've been given the volume. We're given the length. We've been given the radius. This is the length. We got to still calculate density, and now we're going to calculate radius as well. Pause. All right, and here is the solution. In orange, well, first in black is all the stuff that I need for my problem. I got my body-centered cubic, so I got 2 atoms per unit cell. There's my length equation, and there's my molar mass. So I start with my 2 atoms, because it's body-centered cubic, divide by Avogadro's number, multiply by mass, my molar mass, and I get the mass, 2.32, times 10 to the minus 23rd grams. All right, well, this time I'm given the length, so all I have to do to find volume is convert it and cube it. So I convert it using my conversion that I'm doing. I get my centimeters from picometers, and I go ahead and cube that, and I get my 4.32 times 10 to the minus 23rd. Well, I just plug that in for density, and I get 0.538 grams per cubic centimeter for my density. All right, so radius, I have to rearrange my length equation. So I got to multiply both sides by the square root of 3 and then divide by 4. So rearranged, I get this guy. So I just plug in my length, which I was given in the problem, and I multiply by root 3 and divide by 4, and I get 152 picometers. This you can just leave in picometers because it's all good. And that's it. That's all you need to know from chapter 12. There's a couple more problems in mastering, but that's it. So now we start with 13.